Good morning, good afternoon, and good evening to delegates attending from different parts of the world. Welcome to the fourth plenary session of 7th International Conference on Recent Advances in Geotechnical Earthquake Engineering and Soil Dynamics. In this session, we'll be having two keynote presentations one by Professor Elgamal and the second one by Professor Charles Ng. This session will be chaired by Dr. G.R. Reddy and Dr. Vishwas Khatri. Before I hand over the session to chair and co-chair, I would like to briefly introduce our chair and co-chair. Our chair, Dr. Reddy, has vast research and academic experience. He has guided 10 PhD and 41 MTech students. His research areas are modeling techniques for complex structures, structure-equipment interaction, stochastic methods, substructure techniques, etc. He involved in the design of several important critical facilities, including antenna for Chandrayaan project and Gamma Ray telescope, and many other. He has also developed products like dampers, isolator, and absorbers. He developed iterative response spectrum for nonlinear systems. He has 500 publications, including journals, reports, and conference proceedings. He has also authored a book titled Seismic Design, Structures, Piping Systems, and Components, published by Springer. As a president of Association of Structural Rehabilitation, he has developed guidelines. He collaborated in 35 research projects at the national and international level. Our co-chair, Dr. Vishwas Khatri, is currently working as assistant professor at the Indian Institute of Technology, ISM Dhanbad. He has worked on experimental and numerical modeling of geotechnical stability problems. He has authored as well as co-authored several journal and conference proceedings, both at national and international level. With this brief introduction, may I now request Dr. Reddy and Dr. Vishwas to kindly take over the session. Please, sir.
So thank you very much, Dr. Ravi, for the introduction. I welcome, the speakers, invited speakers, as well as the delegates and the organizers to participate in this particular session. So before inviting Dr. Ahmed to give his lecture, I will introduce him. Yes, please. So 1 second. Dr. Ahmed is a professor of geotechnical engineering at the University of California, San Diego. Currently, he is serving as the School of Engineering Associate Dean for Faculty Affairs. Earlier, he chaired the Department of Structural Engineering from 2003 to 2007. He received his PhD in 1985 from Princeton University. In 1997, he joined UCSD after a postdoctoral appointment at the California Institute of Technology and faculty positions at RPI and Columbia University in New York. His areas of research interest include liquefaction and effects on the built environment, large-scale soil structure experimental and computational simulation, sustainability in geomechanics, information technology applications, and the system identification procedures. He is author and co-author of over 300 technical publications and currently serves as editor-in-chief of the Journal of Soil Dynamics and Earthquake Engineering. Over the years, he has consulted and provided professional services in the general areas of geomechanics and geotechnical engineering for a number of national and international organizations. So I request Professor Ahmed to deliver a lecture on nonlinear soil structure interaction and application for bridge systems in liquefiable ground. I welcome Dr. Ahmed to deliver his excellent lecture, and I request all the people to participate and let us get a lot of knowledge from the Professor Ahmed. Thank you very much. I request Dr. Ahmed to start his lecture.
Thank you. Thank you very much, Chair Reddy. maybe before I start, I would just like to update a little bit what you mentioned. I completed my term as Associate Dean and also my term as Editor-in-Chief of the Journal of Soil Dynamics and Earthquake Engineering, which was a great privilege. It's a pleasure to see everyone. I would like to congratulate the conference chair and the organizing committee for the incredible job they have done in preparing this remote event and all the preparations that preceded this when the conference was to be held in person. It's a great honor to join you and have this opportunity to present my lecture. So let me please share my screen.
Yes, sorry for interrupting, Dr. Ahmed. You have 40 minutes. Kindly let us see that you will complete your lecture, so that we'll have some time for interactions, please.
Absolutely. Thank you.
Thanks.
Okay.
Thank you, Laura.
I think you can see my screen now.
Yeah, it's good. Yes, very good. Yes.
Thank you. So I would like to focus today on computational simulation of nonlinear soil structure interaction with some applications, including applications for bridge systems and liquefaction. It's been a long journey trying to develop better tools for analysis of soil structure interaction. And it's still a continuing journey. Where I will leave off, others will continue. So some progress has been made, and I hope to share with you some insights and highlights of the work that has been done over the years. Many researchers over the years have contributed to this work. Some of them are, their names are here on this slide. And of course, over the years as well, funding from many organizations was secured to support graduate students and so forth. So some of the funding agencies are also shown on this slide. In particular, more recently, 3 PhD theses, as you see here, contain much of the work, the recent work that I will present today. So I would like to acknowledge Drs. Jean Lee, Dr. Ahmed-Waeil, and Dr. Jizian Qiu. So why do we need soil structure interaction and the need for an analysis framework? So when this effort started, an attempt was being made to produce 3-dimensional simulation tools tailored for conducting seismic response. And hopefully these tools would include the latest nonlinear structural analysis techniques, for example, beam column fiber elements, hook gap elements, and all other kinds of simulation tools for modeling structural response and soil structure interaction, and also include state-of-the-art nonlinear soil modeling capabilities, include saturated soil modeling logics, and suited for the needs of performance-based earthquake engineering, which includes low levels of shaking, medium levels of shaking, and very strong levels of shaking, and the consequence of these shaking events. And having these tools available in the public domain, including the source code. So this work started more than 20 years ago with the Pacific Center for Earthquake Engineering, where they set up a platform, as you know, known as OpenSees. And over the years, we were able to contribute to this platform by including nonlinear soil response models and fully coupled solid fluid formulations for liquefaction, and along with that, pressure dependent and pressure independent soil models, as you see here schematically displayed in this slide. Again, to get these tools to be representative or more representative much effort has always been taking place related to calibration. So this is some of just an illustration of our participation in the Project LEAP for numerical simulation of centrifuge experiments that were conducted under this project under the leadership of Professors Khatri, Manzari, Ziegel, and Weida, and others. As you see, even with the availability of results from centrifuge experiments and, of course, one-dimensional downhole arrays recorded motions from actual earthquakes, there is still room for getting more realistic outcomes out of the numerical tools when they are applied to three-dimensional simulation, and in particular, as it relates to soil structure interaction, which places additional demands on the level of strains that take place in the vicinity of the structure as the structure pushes and pulls on the soil, as I'll try to show some of that now. So I will try to present some of our work related to three-dimensional soil structure interaction and look at situations where strains are shear strains are relatively small, for example, where equivalent linear analysis might yield reasonable outcomes. And then we'll look at large strains, elastoplastic analysis, and then we'll see some scenarios where the strains are much larger, of the order, let's say, of 10% associated with liquefaction. And then some of the strains, again, as a consequences of liquefaction in the vicinity of a foundation where the soil flows around the foundation with strains that are much larger than 10%. And trying to show this in the context of three-dimensional numerical simulations. So we'll look at the response of an embedded structure and also take this as an opportunity to look at site response away from the structure. And then we'll look at large pile groups. We'll look at a wharf on piles. We will look at three-dimensional bridge systems, including liquefaction. So let's start with site response and embedded structures as in situations, for example, of nuclear power plant containment structures. So in this study, as you see, the soil mesh is very large compared with the size of the structure, which is substantial in and of its own. Because of symmetry, it's a two-dimensional mesh, and the shaking is taking place in this lateral direction. So this is what is shown here as a half mesh. And then with the input motion imparted at the base of the ground, we studied the outcomes if this motion is scaled by 1, if it's doubled in amplitude, 3 times in amplitude, and 4 times in amplitude, to compare the response of fully nonlinear and equivalent linear under these different 4 levels of seismic excitation. We also included a no tension condition here between the structure and the soil, which is a more realistic way to model the interaction. And we had the transmitting boundary at the base. We used this soil model, which is a pressure dependent soil model for our nonlinear analysis. As you know, in the equivalent linear analysis, the work is done by a secant modulus and equivalent damping at a particular shear strain level. And you see here that the reduction in modulus with strain amplitude is quite substantial. For example, here we go down approximately to 20% of initial shear modulus at a strain of 0.3%. So if we look at the free field ground response in the beginning, we're showing here the shaking as it was, and then the shaking when it was scaled to 4 times its amplitude, so that's much higher shaking. We see at ground surface that the at low levels of shaking, as you might expect, the nonlinear model and the equivalent linear yield very reasonable results and very close. The response at ground surface is significantly larger than the response at the level of the base of the structure at 23 meters depth, if you compare this 6 and this 4. And when you go to the 4 times the level of shaking, you see, of course, that because of nonlinear effects, that this resonance peak is much muted and it is spread over the frequency range compared with the low level of shaking. And both the equivalent linear and nonlinear to some degree reproduce this. The only limitation really is that the equivalent linear analysis subdues the high frequency response that is shown by the fully nonlinear analysis, as you can see here in these boxes at higher frequencies. And this might be something that is somewhat important for secondary systems that might be embedded within this, that might be inside of this embedded structure. Okay, so we go now to the response of the structure itself. And since the structure is at 23 meters below ground at its base, and the structure is fairly rigid, the first thing we see when we compare its response to the free field is that at the ground surface, the structural response is much less. Also, the high frequency response, which is a consequence to some degree of site amplification in the upper several meters of the ground, is much reduced. And in general, the response of the structure is very similar to its response at its base at 23 meters depth, which is, of course, something that helps the structure a lot in having lower amplitudes of shaking and response. So the deeper the embedment of the structure is, the less levels of shaking that will be observed compared to the nearby free field, which is good news. Again, this is shown at 1 times the shaking and 4 times the shaking, the same thing where you see the free field is always much higher than the response of the structure, which is similar to its response at its embedded depth. So when we found that the response of the structure is much less this way compared with ground surface response, and the high frequency response is much less as well, we ended up finding that whereas the equivalent linear analysis didn't do as good a job in the free field, it actually did a much better job for the structural response, since the structure does not amplify the high frequency response or is not affected as much by the high frequency response near ground surface. And its response is similar to its response at the base. We found that the nonlinear and equivalent linear comparison is quite favorable for the structure response itself. We also looked at earth pressure, lateral earth pressure on the structure, and some of the observations we saw, since this is a 3-dimensional simulation, is that the changes in the dynamic earth pressures affect this 45-degree part of the structure from the front and the back. And here in this part, since the shaking is only in this direction, this part of the structure does not see much change at all in the static state of pressure. So this is the pressure on the right side of the structure pressure profile. This is the pressure profile on the left side of the structure. And in this section that is in a sense parallel to the direction of shaking, the earth pressure doesn't change very much. The other interesting thing is that the distribution of earth pressure as the soil, in the instant where the soil is moving in this direction, as you see here, takes this shape on the left side of the structure. Of course, there is an inertial force also coming from own weight of the structure pushing on the soil. But on the right side, the soil is also moving away from the structure. And near the top, a gap opens, as you see here, and there is no pressure on the structure momentarily. And then the pressures as a reaction show up on the other on this side and have a distribution that looks something like this, and actually becomes quite high at the base if you think, you know, the base is wedged and pushes on the soil hard, since the structure also experiences some rotation. So when you look at this distribution of earth pressures and compare it with the classical Mononobe-Okabe earth pressure theory, you see that there is really no relationship between the MO analysis and the actual distribution of dynamic earth pressure on embedded structures, as you see here. So in summary, for the ground response, the site response at these relatively low levels of strain, equivalent linear analysis are reasonable, but underestimate high frequency response. And for the structure itself, the high frequency response is much reduced. The acceleration at the top is very similar to its acceleration at the base, which is quite lower than the free field acceleration. And the acceleration response compared well, the equivalent linear acceleration response compared well with the nonlinear counterpart all around, and give a reasonable result that way. And then seismic lateral earth pressure is quite different from the Mononobe-Okabe analysis. Now, moving on to large pile groups. There was an opportunity to look at the behavior of a pile group in a bridge where navigation is allowed in the center of the canyon or in the center of the channel, of the water channel, for this Dumbarton Bridge scenario, for example. And as you see, to allow for this navigation near the center of the channel, the bridge is very high. As you see here, when we go to look at the bridge along its side view, and we look here in the center, we see that these piers are, the deck is 27 meters above water level. And then there is the pile cap, and then 14 meters into the water is where the mud line is. And then the piles are embedded 16 meters into the ground. So between the deck and the mud line, we have about 40 meters of elevation. And so when shaking comes laterally, in addition to the shear force that will be experienced by the pile group, you see that a huge moment will also be acting because of this very large moment arm, and the pile group will be subjected to a very large moment and at the same time a very large shear force. Whereas we tend to study for seismic analysis pile groups under lateral load, as you see in this, as I will try to show in this case, axial loads coming from that moment are much more important potentially, and might actually be the main cause for trouble compared with the shear force alone. So we use this platform, OpenSees PL, which is capable of producing finite element meshes in a user interface to look at pile groups that way. And with a pressure independent soil, elastoplastic soil model, we looked at the bridge own weight effects and the effects under lateral pushover analysis, equivalent to as high as the weight of the deck in the horizontal direction, as if there is a pulse of 1G applied to the bridge. And you can see that the response of the pile group is highly nonlinear compared with its initial response because of the behavior of the piles, obviously, but also the nonlinear soil in this simulation. Moments on the piles in this case were, of course, as you might know, corner piles ended up shouldering much more load than inner piles. This is again a half mesh. And so these are the inner piles, these are the outer piles, and this is the corner pile. And as the level of load increases, you see that the peak moment location is going downwards into the ground because of yield of the soil gradually from the high displacements of the pile from the mud line further down. Now looking at axial forces, just under the own weight, static own weight of the bridge, you see again that the corner piles carry much more of the axial load than the inner piles, and the edge piles also carry higher load than the inner piles, which is of course documented in the literature as an important mechanism because of the availability of more outer soil here to resist load compared with the soil that is shared here by many piles and experiences load from many piles at the same time, and consequently these piles are in a sense end up being in a flexible part of the soil and carry much less load compared with these outer piles and the corner pile in particular. Now if we look at the situation where the pushover just included the horizontal force first, instead of the force and moment together, we see that the loads on the piles increase in the front here where there is compression, increase a lot more, and also turn from being compressive to tensile because of that very large moment, being 3.4 times, for example, the axial load under static load if you know, as a normalizing quantity being a single, for a single pile scenario. So 3 times the load in tension as compared with 1 time the load in compression under just the own weight of the bridge. When we include the moment as well, you can see now axial loads increase to nearly 10 times in the outer pile in compression, and also about 9 times or so in tension. I don't think any pile or pile cap is designed to deal with tensile forces that are of this order. And there is a very high probability, if a scenario like this happens, that there will be separation between the pile and the pile cap. That might not necessarily imply any collapse or any large deformations in the end, because at the end of the earthquake, the pile cap might come back and just sit on this damaged pile head, and there won't necessarily be an apparent permanent deformation, since other piles might be able to continue supporting the bridge, but there can be damage that will later lead to deterioration of the bridge because of the elements and so forth. And it's certainly an undesirable outcome. So the main outcome here is that axial response is potentially much more important than lateral response for scenarios like this, where there is a large moment that is involved. Tensile forces might be quite significant and affect the reinforced concrete response. And the corner piles are most vulnerable, and all these are things that are shown by this 3-dimensional simulation of this pile. Okay, if we look at a scenario of, again, wharfs on piles. These are, types of structures are the prevalent type of wharf foundation in the United States. This is a picture from the Port of Los Angeles. The ship is here, the container ship is here, and the wharf is here. This is a close-up of the wharf, and here is the container ship. And this wharf is supported on many, many piles, as you see here. In cross-section, the piles look something like this. This is the land side, this is the water side, this is the sloping ground under the wharf. This is the deck of the wharf, and these are the piles going into the slope as you see here. So when we looked at the plan view of this wharf, we saw that the pattern of the piles keeps on repeating itself from one end of the wharf to the other. And so that allows that we could take a three-dimensional slice and study it as a representative of the response of the entire wharf from beginning to end. A symmetry slice, if you will, but it's a three-dimensional slice. So this is here the three-dimensional slice. These are the piles, front to land side, water side to land side. And this becomes the three-dimensional slice that we are studying. The soil on the land side, the soil on the water side, the 16 piles that represent the symmetry section of the wharf. And again, doing seismic excitation by shaking at the base, by including here one-dimensional shear beam columns that capture boundary conditions on the right and on the left, which is essentially free field response on the land side, free field response on the water side. So before looking at the three-dimensional response, some people were proposing, and maybe continue to propose, that if someone does a slope analysis without the presence of the pile, and then takes these deformed configurations of the slope at the location of the piles, that this might permit that they can take these displacements and then use soil springs and apply these displacements to the piles. But in fact, when the piles are present in the slope, you see that the configuration of the ground is very, very different from the configuration without the piles. And so to a great extent, that really doesn't work. The piles change the configuration of the deformation of the slope, and this displacement pattern is very different from the pattern if the piles were not present. So here is the deformed configuration after shaking. And it's obvious that all piles, actually, the piles that have a free length, a very large free length, and the ones that have a very small free length, all deform in a similar way because they're all deforming according to the deformation of the slope. And in a sense, it's all an integrated deformation. There is no additional deformation in the front, for example, compared to the back. So in general, to a great extent, the front piles and the back piles undergo very similar displacements and undergo relatively similar moments, which was something, again, where some people were proposing that the front piles, because of their free length, are more flexible, and so they suffer less than the back pile that doesn't have as much free length. As importantly, again, since all these piles are connected to a very rigid deck at the top, because of the deformation of the slope downwards on the land side and upwards on the water side, all kinds of tensile forces evolve in the piles. They're all, again, connected at the top. So you get compression, you get additional tension, and depending on the part of the pile in the softer soil and the part of the pile in the stiffer soil, you get all these kinds of changes. And it's, again, likely that tensile forces might play a very significant role in the integrity of the wharf on pile scenario, compared with just the attention that everyone pays to lateral deformation and consequences of the additional moments imposed on the pile. So what this is what this slice is attempting to say, that in addition to bending, axial loads are quite important and require further attention. Okay, so going quickly to bridge ground systems. Three-dimensional simulation for bridges is actually something that leads to much more realistic outcomes. This was an effort that was done early on, several years ago, and the idea was to try to capture some of the things that idealizations in 2D are not able to capture. So, for example, the 3D pile foundation configuration, the 3D ground response, and the 3D characteristics of the response of the deck and abutments can only be captured if the simulation is done in 3 dimensions. So this was the mesh that was constructed for this bridge in California. And you see the approach, ground approach ramps, you see the bridge, you see here the foundation systems in 3D, and the shaking itself is also done in 3 dimensions. OpenSees allows for, as I mentioned earlier, integration of state-of-the-art fiber element beam column elements to represent the nonlinear response of the bridge structural elements. So along with the nonlinear soil response, you see that also the bridge is modeled also using the latest tools that were available for nonlinear response of the reinforced concrete. And these were tools that are still available in OpenSees by Professor Filippo of UC Berkeley. So at the end of shaking, compared with observation where you see lateral spreading leads to soil going towards the center of the canyon, leads to spreading of the approach ramps also sideways, leads to pushing on the bridge, as you see here, that these characteristics are reproduced, at least conceptually, in this 3-dimensional simulation. And we get a little bit of heave of the soil here since the soil is moving into the center of the water channel, and then settlement, of course, here. And here is that outer spreading of the approach ramps. This is the final deformed configuration of the bridge. You see that there is settlement of the abutments as we observe in earthquakes. There is rotation of the abutment as we observe in earthquakes. There is permanent translation of the foundations in the zones that have moved sideways near the abutments. And then near the center of the bridge, you see that these foundations do not move much. The soil here is not moving much, but the deck itself might be moving permanently and also causing lateral deformations of the supporting piers of the bridge. In addition to what is happening in the longitudinal direction of the bridge, also in the transverse direction of the bridge, there are deformations from the shaking. So the bridge does not deform uniformly in the transverse direction. This is the final deformed configuration of the bridge looking at plan view in the transverse direction. And you see that there are additional consequences to the 3-dimensional shaking coming from the transverse response in addition to the longitudinal response. Okay, moving on to looking at bridges under liquefaction. We have been looking at a few actual bridge scenarios from California, where you see now that the bridge has different structural configurations at different sections of it, and different cross sections of the support of the shear wall or the columns or the piles. And the soil is also not uniform along the longitudinal direction of the bridge. Different soils, according to the borings, idealized here in terms of 3 different configurations on the left, in the center, and on the right of the bridge. Everything, again, for the bridge is modeled with fiber elements. And similar to what we have done for the wharf, we attempted to also take a slice in the bridge in its longitudinal direction. Of course, this slice is not as representative because the bridge is not wide enough in the transverse direction like the wharf, but it also allowed us to observe some mechanisms of the response that are quite significant. In this case, we did shaking using Rinaldi motions from the Northridge earthquake, and it's the important thing about it is that it's a near field motion that has a pulse, a preferred pulse in one direction. And so you will see in a second that this has a consequence on the response of the bridge, in that in addition to the ground deformation near the slopes and the abutments that you expect, of course, the soil to flow towards the center of the channel on both sides, but also, as you see here on the end, the entire ground ends up with a permanent deformation in a preferred direction because of this near field pulse. And if you reverse the input, the direction of the motion, what is positive in acceleration becomes negative, and what is negative becomes positive, this permanent deformation will revert to the other direction. And so what is really happening here and here is a consequence of this overall lurch because of the near field pulse, plus the slope deformations on both sides, and you add these up and you get the outcome. And you can see that, of course, because of this permanent lurch, the deck moves forward permanently this way on both sides, and along with this forward motion, also that slope is pushing on the deck this way. And so we end up with the soil on the right side here pushing to the left. And because of the forces coming from the deformation on the left side and the lurch, the deck moves to the right. And so we end up with trouble here, not only coming from the slope deformation, but also coming from the deck moving in the opposite direction and causing this forward motion at the top, backward motion below, and causing additional trouble to the piles. So these piles are affected actually by what is happening on the other side, not only what is happening in that local slope. And it emphasizes the need to look at response in 3 dimensions. And also looking at the integrated response of the bridge ground system with the whole bridge involved, not only looking at one slope at a time. In the center of the channel, the foundation doesn't move much, but as I mentioned earlier, the deck moves permanently, and that again can result in unseating, can result in large moments on these middle section piles, which of course is something that is not captured at all when people study the left side on its own or study the right side on its own under lateral spreading because of local deformation at the abutments. So this is what this slide is trying to summarize. And in the end, the most important thing is looking at the bridge and the ground as a system, and not looking at one side at a time. As you see from this study, there is trouble on the left, there is trouble on the right. Some of the trouble on the right is coming from the motion of the bridge into to the right, affecting what is happening here. And also in the center of the bridge, the trouble is not coming from the deformation of the foundations, but coming from the permanent deformation of the deck to the right, and where the foundations don't move much. When we looked at what we call a short span bridge, where the 2 slopes are, as you see here in a narrow canyon, close to each other, then we saw significant interaction between the deformation of the slopes. So you see here, displacement of the left slope interferes with displacement of the right slope, and leads actually to much less lateral deformation compared with studying, for example, the right slope, which was the more vulnerable slope on its own. So if you just looked at the scenario of the left slope on its own, or this right slope on its own, the deformation under the same shaking was 5 meters, which only was 2/3 of a meter because of the interaction when the full canyon was involved and there was a slope here on that side. So again, it leads us to think of the importance and the significance of doing a system response and a three-dimensional analysis to capture the more realistic picture as opposed to looking at one section at a time. So some of these tools are available at this website, soilquake.net. And as I mentioned earlier, these tools were developed for OpenSees. More recently, we tried to make some of these tools also available for uses in other codes like FLAC, LS-DYNA, and Diana and Abacus. So you will find some information about this on the SoilQuake link, at the SoilQuake link. And also, if you're interested in calibration and actual data from recorded earthquakes from downhole arrays, we had this data and we have uploaded it for these two locations, and it's available to download at the site as well. So for your own use. I think my time is up. I need to turn this off.
Yes.
Yes, please. Maybe you can. I request you to slowly wind up. Yeah, no problem.
Yes, I am. And then finally, some recent work to look at also geometric nonlinearity is being directed towards a technique that is shown here. So this is a meshless representation as opposed to finite elements that lends itself more to looking at very large deformations with also strain softening soil models that have been recently developed. And this work is ongoing. We're trying to also capture some aspects of geometric deformation in addition to the material nonlinear deformations. And so we would also bring into the picture geometric nonlinearities. Okay, I think that concludes my presentation. Thank you very much.
So thank you so much, Professor Ahmed, for giving a very informative lecture. I request a co-chair to just prepare for a question answer session. Meanwhile, I'll just summarize what I could understand from the lecture of Dr. Ahmed. Co-chair, please get ready for the question answer sessions. Maybe you can have to go through the box where a lot of questions may be there. We can kindly get prepared. Just 1 minute, I'll just try to summarize and say maybe I'll initiate one question. Yeah, it was a wonderful lecture. He introduced, Professor has introduced the subject with containment structure, the effect of equivalent nonlinear analysis and detailed nonlinear analysis, how the difference in the response of the containment, including the soil, and the variation of frequencies and the amplitudes if you take the soil structure interaction and nonlinear effects of the say soil. That he explained very nicely, given a lot of insight of the subject. Then he introduced, he explained on the pushover analysis of the bridges is very, very important because the subject now, I think everybody going for the performance-based design of structures. So soil definitely you cannot ignore. So you have to consider that. So a procedure for doing the pushover analysis and seeing the various levels of performances under earthquake loads, considering the bridge, he has explained very nicely. And a lot of cases with respect to bridges and port structures, he explained very clearly, and is very, very interesting that his lecture says in all the designers, you have to take the nonlinear effects when you want to say that the bridges structures are safe for earthquake loading. So I just to trigger the session on the question answers. Can you please elaborate on the slicing on the bridge when you are taking the modeling and you are making model and analysis? This is a request from my side to trigger the question and answer session so that our co-chair will be ready for the question answers, please. Yeah, session. Yes, please. Dr. Ahmed, please. Thanks very, very much, because wonderful lecture. I learned a lot of things from your lecture, and I also, generated a lot of thinking, how to go about in the future, what is the research we can perform. Thank you very much. Yes, please, Dr. Ahmed.
excuse me, sir, just a small announcement may I make.
Yeah, please, Ravi,
Yeah.
Dr. Ravi, yes.
All the delegates are requested to post their questions under Q&A that is available on the menu bar. And also there is an icon placed over the conference platform. To access Q&A, you need to come out of from the full screen mode. Then only you can be able to access. Okay, thank you one and all. Okay, sir. Professor Elgamal, please.
Yes, I see 3 questions. Should I try to answer those now?
Yeah, please go ahead. I think that yes, Dr. Vishwas, please.
Yes, I think I will.
Okay, the first question is about the pushover analysis on the pile group. And yes, of course, there are road. Yes.
Can I read it for you? Can I read it for you?
Please.
No need. Yeah. In a pushover analysis, a load pattern is applied with increasing magnitude in a single direction. But in reality, there are frequent stress reversal during an earthquake. So what is the reason to trust result from pushover analysis? This is the question posed. First question.
Yes, if there is an earthquake loading, a dynamic analysis is definitely needed. And so what we did with the pushover analysis, because we tried to use as refined a mesh as we could implement on the computer resources we had at the time, dynamic analysis and actual earthquake shaking would have not been possible. And so we resorted to illustrate some of the salient consequences of lateral loading to this pushover analysis. But this isn't a replacement of doing actual seismic excitation. On the other hand, if it is expected, for instance, that peak acceleration of the bridge deck would reach 0.6 G or any other value, there might be a way to apply a force that would be equivalent to the lateral inertial force that would come from a peak acceleration of 0.3 G at pushover, and in a sense see maximum force, under maximum force, what levels of deformation and if any permanent deformation of significance might happen.
I hope the person who posed the question, he got his doubts clear. So second question we are having is, sir, how to decide upon mitigation measure or the design solution for prevention the damage to critical infrastructure during the earthquake using FE simulation? Question is a bit long.
Yes, again, another, please.
Yeah, I think I will repeat it. How to decide upon mitigation measures or the design solutions for preventing the damages to critical infrastructure during earthquake using FE simulation.
Yes, another very good question, similar to the first one, and insightful. You might have noticed that some of the representations that were studied were idealizations. Even though they are 3-dimensional, they still are really not the entire 3-dimensional picture, and they were an idealization in the end. Because again of the difficulties in being conducted more elaborate and more realistic, fully 3-dimensional analyses of large and complicated structures. On the other hand, these simulations permit to some extent also gaining insight about possible mitigation, implementation of possible mitigation measures. So in some of the studies that we have done for the liquefaction of the and its effect on the bridges, for example, is that with that 3-dimensional slice that we used for the representation of the bridge, even though it is not as realistic as modeling the entire bridge, but in this environment, we looked at scenarios where if there is ground modification done at certain locations, what is the outcome? If there are additional piles installed, what is the outcome? And so it was a very good environment and a useful environment for doing parametric studies to see different mitigation techniques and their outcomes. And I hope this answers the question about that the finite element analysis might be useful for looking at also countermeasures and mitigation along with the response of the original structure.
One last question we are having, sir, is how practical are fully 3D simulation in typical design practice?
Very good question as well. And I think three-dimensional simulations, there is no question, remain to be difficult to undertake. And especially for design practice, I see sometimes very, very large three-dimensional simulations. And even though it looks like the simulation ought to produce extremely realistic outcome on account of the very large number of elements and attention to several details. But just because there are so many things that need to be taken care of, and also load stages and construction sequences and so forth, we have to, in the end, keep that in mind and know that any three-dimensional simulation, as elaborate as it might be, still requires engineering judgment. And for typical design, I think it's still very difficult, but maybe for special projects, there is room for it at the present time. And hopefully in the future, more scenarios would benefit from that.
I think one more. Okay, I think one more is there. Okay, some insight. Okay, I think computational resources Professor Elgamal has already shared, so no need to answer this question. Then, what is the limit up to which what deformation oblique strains we can allow in FEM? This is the one question posed.
Yes.
What is the limit up to what deformation strain we can allow in FEM?
Again, a very insightful question. And to some extent, it's really the response quantity of interest is what governs where you might start thinking that numerical analysis isn't providing enough insight. So sometimes if you're looking at overall response, you might get something reasonable. But if you're looking at local response, you have to keep in mind that strains can be very large. And if the mesh is refined further, the answer would change and hopefully improve. If there are nonlinear mechanisms happening between the structural elements and the soil, as much and as hard as we try to capture those, there are other things that are happening that aren't captured. And so if utmost attention is given to all these details, I think the resulting deformations might be realistic. But on the other hand, always think about things that might not be well represented in the finite element model, and that if these things might have an effect on the outcome, then you need to look at that independently of the numerical analysis and use engineering judgment.
So from the Q&A, hopefully Professor has answered all the doubts. So I thank you, Professor Elgamal, for clearing all the doubts of the attendees.
My pleasure. Thank you very much.
So thanks a lot, Professor Ahmed, for.
I think, sir, your mic is muted. Ready, sir?
Okay, over to the organizers. Yes, please. Okay, I think we will move to the next lecture by Charles, Professor Charles. Professor Charles WWNG is currently the Dean of H. Folk Ing Tong Graduate School, CLP Holdings Professor of Sustainability and Chair Professor in the Department of Civil and Environmental Engineering at the Hong Kong University of Science and Technology. He's the President of the International Society for Soil Mechanics and Geotechnical Engineering. I think currently also is continuing as a president of this particular society. Professor NG earned his PhD degree from the University of Bristol, UK in 1993. After carrying out a period of postdoctoral research at the University of Cambridge between 1993 and 1995, he returned to the Hong Kong and joined the university as assistant professor in 1995 and rose through the ranks to become a chair professor in 2011. Professor NG was elected an overseas fellow by Churchill College, the University of Cambridge, a fellow of Royal Academy of Engineering, a fellow of the Hong Kong Academy of Engineering and Sciences, and a Chanji Zhang Scholar, chair professorship in geotechnical engineering. He is also a fellow of the Institute of Civil Engineers UK, the American Society of Civil Engineers, and the Hong Kong Institute of Engineers. So it is very great pleasure to welcome you, Professor Charles, for this particular session, and is also a great pleasure to introduce you to the the delegates as well as the organizers and others who are participating in this particular session. So I welcome again Dr. Professor Charles to start your lecture. Thank you so much. Thank you so much.
Thank you, Chairman, for your kind introduction. And if I may, let me share my screen.
So I request you see that your lecture is completed 40 minutes. I generally I don't try to interfere. Intervene in your lecture. So kindly take care of 40 minutes so that we have time for discussions. Thank you so much. Thank you so much.
Thank you. And before I start, I would like to thank the organizing committee for inviting me to make this presentation. And also, I would like to thank my co-authors, Dr. Tai and Dr. Wanswen, and for their contribution to the work I'm going to present. And due to the time constraint, as the chairman said, and I decided to move out anything to do with tunneling in my presentation. But in the written submission, and you will see in our paper, we cover both pile foundation and also tunneling, subject to normal faulting. So here is the content of my presentation. First of all, and I would like to briefly introduce my university because, and as we all know, that the objective or function of a conference is to exchange technical information, but also to encourage collaborations among the universities, among the researchers, and also engineers. So I decided to give a little bit of background or introduction to my university so that I hope, and if you're interested in our university, perhaps we can establish different forms of collaboration. And then I'll move on to a background of the research I'm going to present. And just in case you are not that familiar with geotechnical sensory modeling, and which is the main tool that I use for our research, I'm going to present today. And then I'll move to show you say 3 sort of examples and using geotechnical centrifuge to solve different type of problems, including forensic engineering to investigate collapse of building in Shanghai, embankment widening using a 4X robot, and also a recent development of an environmental chamber for simulating climate change effects. Then I'll move on to 3-dimensional and centrifuge and numerical modeling of pile foundation subject to faulting, and present to you our interpreted measure and computer result. And hopefully I still have time, then I'll come to conclusions. And here's area photograph showing Hong Kong. Hong Kong is very small. If you landed to this airport here on the left-hand side, then travel to the east about 40 minutes, then we reach our campus on the east coast. And here a couple of photographs showing our campus and different view. I hope you agree with me. Our campus indeed looks very beautiful, and our university was established about 30 years ago, 1991, and we have 4 major schools. Our university is small, by the way. We only have 4 schools, about 10,000 undergraduate students and 50,000 postgraduate students, including 3,500 master students, MSc students. But in the geotechnical group, we are sort of pretty large. We have about 60 PhD students and 30 MPhil students. Although we are young, but we are sort of globally recognized for the time higher education young university, which means the university has to be below the age of 50. Then actually 2020, we ranked #1. And then QS ranking also, we ranked #2 in 2011. And good news perhaps to share with you is we are building a new campus in Guangzhou, and which is twice the size of the one we have in Hong Kong. And the Guangzhou campus is located only 27 minutes by high-speed rail from Kowloon to Qingsheng Station, which is very close in the sense by a fast-speed train. And English is an instructional language to be used in the campus mainly. And the new campus will be open next year, September 2022. And eventually we will have 6,000 postgraduate students versus about 2,000 research students in Hong Kong. So it's 3 times bigger in terms of research capability, in other words. And we will have about 4,000 undergraduate students, but undergraduate will start from year 3, okay? And then we will gradually increase to 4,000. And there's a couple of pictures showing the new campus and from the architectural drawing. And that's how they should look like. And at the moment, we are recruiting 150 academics, means professors, assistant professors to full professor above, okay? And also we are recruiting about 1,000 research students now. So if anyone interested in the audience interest, please go to our website. And talking about collaboration, and no matter whether it's Hong Kong campus or Guangzhou campus, we do encourage and exchange programs, meaning students from India can come to Hong Kong for 6 months, and our student can go to India for 6 months. And that will be fully funded by our exchange scholarship, and which now at the moment is about $1,200 per month, and is enough for a single research student. And also we have full scholarships for full-time students, depends on the types of scholarship, ranging from $2,000 to $3,500 per month. Okay, we also have a dual degree opportunity, meaning, say for some I.I.T can if they're interested, can sign an agreement with our university. We have a dual degree program, meaning students can spend on each campus 2 years and to get a dual degree. And here's my research group, if you like. Okay. Oh, sorry. Pardon. And you can see actually my group is very international. I have students from South Africa, from United Kingdom, Bangladesh, Thailand, and India. And he graduated 1 year ago. And then and also Iran, for instance. Okay. And also I'm students from Pakistan and also from couple of African countries. So now let me move on to the background of the research I'm going to present today. And here are just a couple of pictures and showing a stadium in Turkey, which was hit and crossed by a normal fault, causing the vertical offset of up to 2.5 meters, causing a lot of damage, you can see here. And Turkey is not the only location subject to earthquake and disaster. And this is a picture, just 2 pictures taken in Taiwan and Chichi earthquake, and which is quite notorious and around the earthquake community. In 1999, again, you can see their fault ruptured over building over there. And also this picture again taken in Taiwan and due to the Chichi earthquake and hitting the one of the continuous rigid foundation supporting the high voltage electricity pylon. More pictures from Chichi earthquake, and again you can see the damage of a 4-story building resting on a relatively flexible foundation, okay, by a thrust fault. So our design challenges and research objectives, actually the result I'm going to present to you actually come from actually initiated about 10 years ago by Beijing's city government. They really want to know, okay, for example, what is the influence zone at the ground surface due to fault movement, okay. Second question we were asked is what are the remedial actions can be taken for existing pilot foundations? And what are the design criteria for new pilot foundations? And what should we do to rezoning for urban cities in earthquake-prone region or zones? So those are the design challenges we were imposed by the Beijing city government, and that obviously become our research objective. So we were commissioned to carry out over 30 geotechnical sensitivity tests. And this is a picture showing the interrelationship between sensitivity modeling, numerical modeling, and field monitoring. So geotechnical sensitivity is just one of the 3 tools that we use, okay, to tackle earthquake design problems or to verify new theory. So today I'm only concentrating geotechnical centrifuge and numerical modeling here. So what is the geotechnical centrifuge modeling? Just in case you are not that familiar with, I will just very briefly to introduce to you. The basic principle of geotechnical centrifuge modeling is to recreate the stress conditions that will exist in a full scale, we call prototype, okay, using a model of greatly reduced scale. And how can it be done? This is done by subjecting model components to enhance body force, which is provided by a centripetal acceleration. So you can see here R omega square, centripetal acceleration, and conventionally equated to number of times of the Earth gravity. So NG. So NG is my surname. Now you understand why I do centrifuge, because my surname is NG. And mathematically, we can easily show that P subscript P stands for a prototype stress, okay, or initial stress, sigma, and in the field, it's rho g HP. And in a centrifuge, we can reduce the, say, dimension height, for instance, by n times. Then what you need to do is just increase the G level by n times. So you can get back the rho g HP. Okay, so the principle, as I say, is extremely simple. Now, therefore, the centrifuge is suitable for stress-dependent problems, such as consolidation, soil structure interaction problems, and like the presentation given by Professor Elgamal, okay, soil structure interaction subject to earthquake, okay, and also liquefaction and slope stability, etc. Now, from a theoretical point of view, it's very, very important, okay, to get the stress right before we carry out experiments. Now, here's a plot of E log P curve, okay. For specimen A and B, they have the same Y ratio, that means same density. But if we carry out model tests at 1G in the lab, that means low stress, here A, then the soil may contract, so the soil may dilate to the critical state line. That means we will be on the long conservative side versus the actual stress in the field, which we can represent by point B, is a high stress, okay? Actually, when you shear B, then you can contract towards critical state. So we get the opposite result, but on the long conservative side. That's why we must get the stress right before doing experiment, okay? by subjective, let me go back, sorry, I beg your pardon. By increase the stress state from 1G to high G, so that the stress state at B is almost identical to the field. Right. Of course, any physical model test is subject to a number of scaling laws, okay, if not all. And one of the typical and most useful one, I would say, is consolidation, for example. Then, which is the time factor here, prototype divided by model is n squared. So that means if we carry out one-day consolidation at 150 G, which is our optimal capacity of our centrifuge, then it will be equivalent to about 62 years of consolidation time. And in the interest time, I will not go to detail about all this to bother you. So just quickly to introduce four major principal applications. One, modeling of prototypes such as slopes, tunnels, liquefaction, earthquake-induced problems, consolidation, etc. And recently also increasing use of offshore engineering such as wave and wind loading on wind farms, for example, and investigation of new phenomena and mechanisms, okay, such as explosion, plate tectonics, and again, recently, debris flows, climate change events, energy exploration, such as exploration of shale gas and methane gas, methane hydrate, for instance. And also we can use it as a numerical, similar to numerical tool to carry out parameter study in centrifuge. But I think the most important use of centrifuge, actually to me, is to calibrate numerical models and methods. Especially now the computer is so powerful, okay? How do we know our calculated results are correct? Okay. Now, very often I heard people say, okay, we calibrate against case history. But I do have a word of warning, okay? And here we have field observation and we have computer program. When we get a good match, if we ask ourselves carefully, what does that mean? Okay. I think we have to be very, very careful to think about it because, okay, in the field, we have a lot of uncertainties, okay? That's why the contractor claim the client use the word unforeseeable ground conditions, right? When in our numerical analysis, we assume K0, we assume water table, wherever it is, boundary conditions. And usually we assume, actually we don't know, right? And also we have a measurement errors, construction uncertainties, for instance. On the modeling side, numerical modeling side also, very often we assume, okay, and stress and strength, strength and stiffness, okay, is isotropic. Very often we ignore anisotropic phenomena in our modeling, right? We also assume the permeability is isotropic very often. And also we assume there's no coupling effect between stress and flow. So the good match in some way, I would say is quite fortuitous, okay, in some ways lucky. Now, I'm not saying numerical modeling is not good, okay? I'm just saying we must be very careful. Then how can we do better? My suggestion is we must calibrate, before calibrate case history, we calibrate physical model tests. Now, although 1G model tests cannot represent full scale, okay, stress, but 1G test still is very useful because for example, as I said, under low stress dilate. So if your model or model procedure or your model parameter are any good, should be able to capture the dilatancy of the event, right? So my suggestion is we go for the calibration of physical model test first before you calibrate a case history. Now, model tests in some ways good in the sense, although again, model tests cannot truly represent what happened in the field, cannot. But we almost know everything what we put in our model, our physical model. So there's no much uncertainty in our model tests, unless your student deliberately want to fool you, put a stone or a rock, okay, into your soil model. That's different matter, of course, right? So in theory, we are supposed to know everything in our model tests, so that gives you a lot of confidence, okay, provided your test is conducted properly. So this is my suggestion. Anyway, so this is our centrifuge in Hong Kong, and especially in 2001, and it's a beam centrifuge. And when you spin up 8.4 meter in diameter, and can run to 150 G, and for earthquake problems, actually we in 2001 actually that was the first one by ISO checking table and mounted on centrifuge, and we successfully did some tests and published in different journals. And also we have a 4S robotic manipulator. Later on, and you will see this baby in operation. Okay, and in one of the example I'm going to give to you. Okay, so if I may show you one first example, which is a forensic engineering to investigate. Actually, we were commissioned by a client in Shanghai to investigate the building collapse over there, and which is the building collapse you can see here. Okay, and there's a closer view of the collapsed building, and you can see the picture actually during the collapse. What happens? Also, just immediately before the collapse, what happens? This is a collapsed building, obviously. Then there was a bad filling on the right hand side, and then excavation on the left hand side. So this is a schematic diagram. Okay, let me. I don't know what happened to my mouse. Looks like hang up. Okay, looks like coming back. Okay, so immediately before the collapse, there was a filling up on the right hand side and also excavation on the left hand side simultaneously. So after the building collapse, obviously different parties blame each other. That's why we were commissioned by the Shanghai government to investigate what causing the collapse. Okay, but anyway, I will not go to detail, but I just show you a video. Okay, and in order to save time, maybe I just go back to a. Okay, so I guess you can see I'm moving my mouse to speed up the present. So we idealized the geology in Shanghai, and what you can see here is a model pile, and there's a building. Actually, we scale almost everything of the problem. So you can see the building of the ground beam here. Okay, there's a shear wall you can see from the top, and insulation of the building in the central container. Okay, and now this is a video taken during one of the tests. Okay, so let me stop here for the time being. So we use a hydraulics actuator to simulate the filling of the surcharge on the right, and also excavation on the left. We're using a string out the heavy fluid, which is equivalent to the density of the soil. So this is the last stage of the test, if you like. Okay, you can see the building is moving and moving and then collapse. Okay, so if I may just replay a little bit. Okay, now then if I go back to the presentation mode so that I can use the mouse. Okay, and so now you can see the upper diagram is the collapsed building in a centrifuge. The lower diagram is the collapsed building in the field. So I hope you agree with me. They look almost identical. And actually, after the tests, we can also take. Actually, we can carry out very detailed investigation where the piles were broken and how they were broken, and so on. Okay, so you can see that a lot of detailed analysis here after the test. And also we can invest the mechanism. So if you are interested in this work, and it's published in Geotechnical 2019. And now another development, actually we use a robot to simulate or the whitening of a embankment. Okay. Again, let me, in terms to save the time, so I will just speed up. So we use a robot and we design this. Okay, let me explain a little bit. We all know that in order to whitening of a embankment, then very often we put piles to support this new parts of the embankment, and the pile is obviously try to minimize the settlement of this embankment, new parts of the embankment caused by the consolidation of soil clay underneath. So now the question is, what should be the pile spacing, for instance, and should we use a geomet and so on and so forth? Okay, so in order to simulate this, of course, one can do three-dimensional numerical modeling, but as I already explained, we need to some sort of physical test to give us confidence the numerical modeling results in some way are reasonable. So we were asked by clients in the mainland, excuse me, to carry out a physical model test. And so this is the model part. It saves time. I will, okay, I skip that. So now this is the actually using a robot to simulate the the embankment construction. So this part here is the existing embankment on the right hand side, and now the embankment is being built, okay, bit by bit, layer by layer, so that we can properly control the speed of the construction, okay, in a centrifuge, which will mimic what actually happened in the field. And also we can control the density of the filling material in a very precise manner by using a robot. Okay, so this is almost the final touch of the construction. And during the construction of the new parts of the embankment, then pore pressure and SO strain and bending strain of the piles were monitored. Okay, I will skip that in the interest of time. Okay, and then, so let me move on to the third example. As we all know that nowadays the effects of climate change and become more and more evidence, okay, or severe, if you like. That's why we develop our sort of an environmental chamber in centrifuge. So what does that mean? Means we can control relative humidity in the chamber, and heating and cooling unit means control temperature, and rain nozzles control rainfall intensity and duration, and fans means able us to model wind. Okay, sorry, let me go back. Okay, and then we have infrared and ultraviolet light to control heat. Okay, so in our centrifuge. So here's a picture. Oh, sorry. So here's a picture showing the actual test in one of our experiments. Okay, so now you can see the humidity nozzle is being used. I use high resolution camera to measure the surface deformation and so on. And if you're interested, this published in Geotechnical Letters 2018, and that gives you much more information than my presentation here. Okay, and I don't know why my computer play up a little bit. Maybe we have to wait for a little bit, couple of seconds. Now, actually, nowadays we use this environmental chamber to study freezing and flowing and effects on slope stability and also on an embankment.
What happened?
Like, let's see on my laser pointer.
Yeah.
I guess now it's back to normal. Is it correct?
Yes, yes.
Okay, good. Okay, so now let me define the problem I'm going to so discuss with you. Okay, and so what we are looking at is it's either a single pile or a pile group. Okay, which is a 1x3 pile group. This is a plan view show here. Okay, and the location of this pile group and so is defined by the coordinate x in the horizontal direction, and also depth is that direction, and y is the second y-axis into the screen. And there's a very important dimension called S. S is measured from the free field rupture outcrop to the edge, the far end of the pile group, because this is defined as S in the x direction. And the width of the pile cap is called B. Okay, and we are going to use this dimension later in a minute. And as I mentioned right at the beginning, and I will not discuss anything about tunneling in this presentation due to time constraint. So what you are seeing here on the left is our model container, which and a single pile is installed, okay, in the container. So the model pile in prototype scale is a square pile, 0.65 meter, okay, on all sides. So it's a square pile, 0.65 meter. And the embedded depth into the soil stratum is 15 meters in prototype. Now the tests, all the tests I present today, and those tests were conducted at 50 G, 50 times gravity, okay? And on the right-hand side here is the 1x3 pile group, okay? And you can see here on the left, we call PF on the footwall side, and for the hanging wall side is PH. In the middle is called PB, okay? And for simplicity, we use Toyota sand, dry Toyota sand, and in all the tests, okay. And obviously, we work on the effective stress principle, so it doesn't matter whether saturate or unsaturate. Sorry, saturate or dry, and we just work on the effective stress principle. So that's why we can simplify the problem without worry about the pore pressure here. And of course, our objective is not to study how the pore pressure dissipates in our experiment. Okay, that was not the objective. Okay, and then we use an LVDTs and also PIV whatever system to measure the settlement of the piles and also horizontal displacement of the pile, etc. Okay, and in the time I cannot go into detail. And now, very importantly, is the model container. How can we simulate the fault movement? And there, I guess most of you know that there are two types of boundary conditions we can simulate. One is the one I just showed here, is horizontally, kinematically unconstrained boundary. Okay, and also we can have rigid boundary. So for this horizontal kinematically unconstrained boundary, is we allow the soil body here on the hanging wall side can move freely horizontally and vertically versus a rigid boundary. Okay, but today I'm not going to present the rigid boundary test, but if you're interested, you can see from this Geotechnical letters published in 2015. Okay, they compare the effects of different boundaries on the performance. Okay, today I'll only report on the sort of horizontally, kinematically unconstrained boundary result. And actually, those are the two model containers. One on the left-hand side here, ready to be tested. On the left-hand side is the single pile SP, single pile here. And here is a pile group on the right-hand side, okay? And the downward fault movement was controlled by there's a hydraulic cylinder hydraulic actuator beneath this loading pattern. Okay, and then during the tests, we and create a fault movement in 5 stages. Okay, and for each stage, we represent in Polar scale 0.4 meter, 0.8, 1.3, 1.8, and 2.1 in this vertical direction. Okay, and before we allow the fault movement to take place, we apply and actually deduce working load for each single pile and pile group. So in other words, vertical load we apply vertical load first, then we allow for fault movement to take place. Okay, and after spinning down the centrifuge, then post experimental and observation were made, and then all the deformation and also the bending moment and on the piles and also the pile cap and actually were measured during the test. In addition to centrifuge, we also carry on numerical simulation. Okay, and so what you're seeing here, the upper 2 picture here, plan view, this is a single pile, and this is the elevation view of the single pile. And the single pile actually is located on the footwall side. And the lower 2 diagram is for the pile group. Again, this is a plan view and this is the elevation view. And here are the 3 piles. And this is the PF pile, and this is a PB, and this is a PH. Okay. And actually, we use the continued model is the one actually given in the flat 3D. It's a string softening more Coulomb with more Coulomb failure criteria. And obviously, this is continued model actually is greatly simplified. Okay, cannot taking account of string dependence stiffness, for instance. But we think it's probably good enough, okay, for our back analysis and also for our numerical parametric studies. And talking about parametric studies, so this is our plan for the parametric study analysis. And there are 2 series, one for single pile, the other one for pile group. Okay, and what we are trying to study is to answer the 4, remember the 4 design challenges and objectives. Okay, so we in our numerical model, we let the location, we don't change the fault location, but we change the pile group location ranging from negative S to positive S. Okay, so that's why you can see here negative 15.5. Okay, this is S. Okay, and so on to positive 31.5 meter. Okay, so there's a range for the pile group, and similarly, there's also corresponding analysis for single pile, also from negative S to positive S. So now let me show you some results. Okay, and this is the development of ground surface settlement. Okay, induced by faulting. On the left hand side is single pile group single pile test, and on the right side is a pile group test. Okay, and we are seeing the horizontal axis is the distance to free field rupture outcrop. That means X. Okay, remember the horizontal distance defined as X, and here's a settlement. And this curve here is the corresponding measure. The open circles are the measured numbers. Okay, corresponding to 0.4 meter of and downward fault movement. And this one here 0.8, 1.2, 1.7, and 2.2. Okay, and similarly, and this is for the pile group. And then what we find actually in terms of ground surface settlement can be reasonably represented by an error function. Okay, here I show you in here. And so obviously, but the coefficient of the error function then depends on whether single pile or pile group, also depends on the magnitude of the fault movements. But broadly speaking, and that can be a very simple tool to be used to for zoning of the surface, ground surface of any urban city. And here on the right hand side here, a picture compare the mechanism between, this is an observed mechanism in centrifuge test. The upper one is single pile test, and for the single pile, and this is for the pile group test. Okay, on the right hand side, there's a numerical simulation here. Again, this is a single pile, and this is the pile group. Then what you're seeing are plotting of plastic shear strain. Okay, you can see well developed at the fault location here. And also you can see the pile group bend and also tilt towards the right hand side. Now, one thing interesting finding is here is actually there's, although the initial fault direction actually we designed to investigate 70 degrees, okay, but actually the fault propagation is deflected to 80 degrees, okay, and then we suspect it's due to the dilatancy of the sand. That's the way used. And here, a series of pictures. This left-hand side here is the settlement of the normal fault versus the displacement of the single pile test. And this is a pile group here. Okay, let's start with single pile. Then we can see the settlement of the single pile. The black solid symbols represent the measured numbers, and the computer ones are the open symbols, represent open symbols. What you can see here, for the single pile, actually, the vertical settlement and measured vertical settlement actually compare well with the computer settlement using the flat 3D program. And the magnitude, settlement magnitude increase as corresponding with the magnitude of the normal fault. Okay, but interestingly, what you see here, the horizontal movement actually is independent. Okay, so you can see here is independent of the magnitude of fault movement. So what does that mean? It means there's a rigid body translational movement horizontally. Okay, and that's a mechanism that we can identify. And how about the pile group here? Okay, then the right hand side of the two figures are both showing the piles performance in the pile group. And so for each one, again, it's using the same symbols, notation here. Solid ones represent the measured, and the open circle represent the computer values. Although the measured and computer are not identical, and actually the computer one tend to predict more than the measured ones. But the general trend you can see actually for the pile group, okay, this is different, quite different from the single pile. For the pile group, actually, the settlement or the normal, the settlement of the vertical settlement of each individual pile is corresponding, in some way corresponding to the settlement of the normal fault. Okay, when normal fault increase and E increase, and also the difference between the measurements also increase. Now for the horizontal displacement of the pile group, different phenomena can be observed. You can see here all three piles, okay, measured ones here, they almost fall on the same line, and this all three piles from the computer results, again, they all fall on the same line. Okay, so what does that mean? Again, similar to the single pile, actually the horizontal movement in some way is sort of translation of rigid body movement, but the vertical ones, okay, is different. It actually is subject to subject to tilting and also subject to bending. Okay, in addition to translational movement. So obviously, because of that, then we induce extra bending moment in the pile cap and also the pile SO pile load. Okay. Now let's move on to here's a plot of pile displacement versus the normalized distance away from this free field fault location. Okay, so S divided by DD is the diameter of pile, and for the pile group normalized by the width B, okay, of the sorry, the breadth of the pile cap. What you are seeing here, and certain three distinct zones can be identified. For example, in zone 1 here, what you can see here, there's no much. So if the pile is located in this zone 1, okay, then basically, no matter what the fault movements is about, actually, there's no much movement. But if the pile is located in zone 2, okay, which is -10 to about 3, okay, then you can see actually about 0 location at both the tilting vertical settlement and also,
sorry for intervening.
yes,
Charles, hello?
yes, yeah.
Please, please.
Okay, I will do my best. Okay, so you can see there's 3 distinct zones can be identified. Okay, and this is transition zone and creates a larger differential settlement, and that's what the designers should be pay attention to. Okay, once you go beyond the zone to go to zone 3, then you can see that actually the pile settlement is identical to the applied fault movements, and horizontal is half, and tilting is further. Actually, not much tilting in this zone here. So this is relatively safe zone, if you like. Okay, and similar picture also emerged in the pile group. Okay, so the take home is there's 3 and distinctive zones can be identified. Now we were looking at the settlement, but also we can look at the pile loads in each pile of the pile group. Again, 3 distinct zones can be identified. Now remember the pile cap actually. The surface load is applied to the pile cap before fault movement is allowed to take place. So this is the working load is about 1100 kilonewton. You can see within zone 1 there's no change. Okay, and then but within the transition zone here, okay, and different piles. So here represents 3 different piles of the symbol here. So within this within this zone, the pile subject to change from compression to tension, for instance, for the PP pile. So this is important, very important for the designer to think about how to take care of this tension, okay, or even additional loading, compression, okay, if the pile group is located within zone 2. And for the zone 3, there's no much change. There's no redistribution of axial forces. Okay. And again, for the tilting theta, the same thing. Okay, it's only the zone 2 is affected. Okay, so the initial time will not go through that. Now, for the bending moment, again, it's very clear. This is for the PF pile, PP pile, and PH pile. Okay, the zone within the zone 2, if the pile group is within zone 2, and actually the bending moment can exceed about 6 times the design ultimate capacity of the individual pile. So definitely designers should be paying much attention to if your pile is within the zone 2. Okay, so let me just quickly summarize what we sort of identify. Certainly, for designers, one is very clear. There are 3 zones can be identified. One is called safe zone. I call zone 1. There's no significant displacement or tilting or settlement need to be aware about in zone 1. But zone 2 is the transition zone. That's where the trouble zone, if you like. Okay, and definitely the designers should pay attention if your pile foundation is located in this zone, or if you try to plan your zoning for buildings, etc., then you have to pay attention whether your zoning fall within the this transition zone. And then the last zone is a translational zone. It's a rigid body zone, if you like. Okay, and there's we see a displacement and translationally, but without tilting, for instance, for the pile group. And the demarcation of the 3 zones is not affected by the magnitude. Okay, that's important by the magnitude of form movement. That's good, and also it's good news. Okay. And here, just give you more detail and elaboration of in the transition zone, the tilting and associated bending moment, okay, of the power we investigate, which the peak value. Okay, the transition zone is always a problem. Okay, and also the tilting of the power can exceed the ultimate allowable limit imposed by EC Euro 7, for instance, and the maximum bending moment, okay, of all piles in the transition exceed, okay, can up to 5.8 times the ultimate capacity. So obviously, increase of thickness or reinforcement should be considered in the design of the structural capacity of the pile, and also pile cap. Okay, and the computed tensile maximum tensile force in the middle of the pile group. Okay, that's PB. Okay, exceed the ultimate tension capacity up to 57%. Again, the tensile stresses must be taken into consideration in the design. Here's a list of relevant, I would say, 8 publications. And if you are interested in the work I just present, please just take a quick look. And if you do need these papers, and let me know. And thank you for your attention, and I apologize for a bit of overrun of my presentation. Thank you.
Oh, thanks, Professor Charles, for giving a very elaborate lecture on the centrifuge test, considering the 5 pile foundation subjected to the normal faulting. I request Dr. Vishwas to have quick questions. Maybe I hope organizers will allow for 5 minutes. Professor Ravi, is okay 5 minutes for question answers?
Yeah, 1 or 2 quick questions, sir, because our other session is going
on. Yeah, please, Dr. Vishwas.
Started.
Yeah, Dr. Vishwas, please go ahead. Question answer sessions.
Till now, I think I have not received actually the question which is available, that is from the old session.
Yeah, maybe I think I'll just summarize a given very wonderful lecture by giving introduction to the Hong Kong University, then also given a lot of pictorial presentation of various actual structures subjected to the normal faulting, how they behaved. Then he introduced, about the centrifuge test, also, shown the test on the structures with the pile foundation with the horizontal excitations. Then he focused on the normal faulting effects on the pile foundations. It was a very, very learning lecture, and it is very.
May I say something? Thank you for the organizer for inviting me to this presentation. And also I'm very glad to see my good friend and Professor Elgamal here. And I listened to his presentation, and his presentation also very interesting. I hope we can develop some collaboration, physical and numerical modeling together. Professor Elgamal visited our campus some years ago.
Absolutely, absolutely.
Yeah.
My pleasure.
Yes, yes, please. Dr. Vishwas, do you have any questions, Dr. Vishwas?
No, sir. I have not received any.
Okay, I have a small question to Dr. Charles. One is when you have a horizontal excitation.
Sorry, I can't hear
it. Frequency.
Sorry, there's a connection problem here. I cannot. Sorry, I think there's no connection. There's a connection problem.
Dr. Reddy, there is some network problem at your end.
Yeah, I cannot hear.
I think
his face is freeze.
No problem.
Maybe he can write to me. Okay, I don't want to hold
later. If there are no questions, I think I thank
yeah,
okay.
I think Dr. Reddy has thanked all of you.
Just I wanted to.
Yeah, please.
I have also used the centrifuge data. Nice to see that. I have worked one problem in my PhD, that is on scale effect on the foundation problem, where I have used the centrifuge data, and ironically, I have also used the Toyota sand only. So this was just nice to see again revisiting the old things.
Yeah, after COVID-19, you are most welcome to visit us.
Yeah. Thank you, sir.
Thank you.
Yeah. may I take the session, Dr. Vishwas?
Yes.
Yeah.
Yes.
Okay, thank you. On behalf of organizers, we thank our esteemed speakers, Professor Elgamal and Professor Charles NG. It's indeed a great pleasure to be part of this particular session. And Professor Elgamal is actually a teacher of my teacher, Professor G.V. Ramana. Thank you, sir. Thank you very much. And also we are very much honored to host Professor Charles NG. He is a president of ISSMGE. It is International Society for all the soil mechanics engineers. So our Indian Geotechnical Society is a part of ISSMGE. Thank you, sir, for sparing your valuable time and addressing our August audience. Thank you. And I also thank Dr. Reddy and Dr. Vishwas for nicely conducting the session. Thank you, all the participants for participating. And now I request all the participants to move on to the parallel sessions, which are going to be started now. Thank you, sir, one and all.
Thank you. Great to see you all.
Thank you.
Thank you. Nice to see you all. Thank you.
That was nice talk.
Yeah, thank you. And you gave excellent talk too. So let's keep in touch. Okay, hope to meet you soon.
Yes, look forward.
Yeah, take care. Take care, everybody.
Bye-bye,
Thank you.
everyone.
Bye-bye.
Bye. Thank you.
Bye.